I'm with the Office of Advanced Reactor Technologies. I'm going to be talking this morning about two different specific subtopics dealing with materials and components for advanced reactors. First, I'll get in my soapbox for a second, make sure everybody understands my belief and our belief that structural materials are critical for advanced nuclear reactors. As a result, DOE is supporting the development and qualification of advanced structural materials since they are critical to the design and deployment of advanced nuclear reactor systems. Specifically, we are focused on high and very high temperature gas-cooled reactors, HTGRs and VHTRs, and sodium-cooled fast reactors. But we are also looking at salt-cooled high temperature reactors, both the molten salt reactor in which the fuel is dissolved within the coolant, and the fluoride high temperature reactors in which there is a liquid salt coolant but a solid form fuel. And lastly, the lead and lead bismuth cooled fast reactors. Now, the structural materials for these systems have to perform over the full design lifetimes for the various assorted components, things like pressure boundaries, internals, heat transfer components, etc. So the performance of the structural materials for those components for the long times and high temperatures and environments required are being examined by Advanced Reactor Technologies program. This work directly supports the work that was outlined in the R&D plan submitted to Congress in 2010, specifically the two criteria to develop improvements for affordability for new reactors and develop sustainable nuclear fuel cycles. Anyone interested can take a look at that report. So the ART program is including advanced materials R&D, and that includes primarily work that we're looking at on graphite, on improved high temperature alloys, and on ceramic composites for the various assorted advanced reactor systems. And a couple of examples of these are the advanced fast reactor, the AFR100 system. It's a fast sodium-cooled reactor system, 250 megawatt thermal, 30-year life core, and 60-year total life system. Another one of the high priority systems example is Reva's high temperature reactor. It's moderately conservative. It's only a 750C outlet only, I say. Some of the high temperature, very high temperature systems are higher than that. 625 megawatt thermal with a steam generator, and plant life is 60 years. Additional systems I won't go into in detail, but are looking at high temperature reactors cooled by both liquid lead and, as I mentioned, the salt cooled systems. So there are two different topics I'm going to talk about in this. One of them deals with materials compatibility for high temperature liquid cooled reactors. And in particular, we're looking at those for salt and lead-cooled reactor systems. And the second one looks at detection, evaluation, and predictive models for degradation of 6-SiC composites. In the first one of these, we're really looking at the predicted lifetimes as limited by corrosion for the various materials that are within the ASME code, and if that cannot be sufficient for the types of systems that are being looked at, what can be done about it. In the second case, we want to understand what the basic failure mechanisms are and life-limiting conditions for 6-SiC, as well as predictive methods, and to support the current ASME rule development that's going on within ASME Section 3, Division 5. Oh, I have extra things to come in here. What a treat. All of these reactors are part of the palette of Gen 4 reactors. And there are 6 of those: the high temperature reactor, the molten salt reactors, both fixed and dissolved fuel variants, sodium fast reactors, supercritical water, gas fast, and lead fast reactors. And of those, we're addressing materials for all but the supercritical water reactor and gas fast reactor. DOE programs are not currently addressing those. And the materials classes that we're looking at are primarily looking at the composite materials and the metals for those. The metals we are looking at for the corrosion effects with regard to the molten salt and lead cooled systems, and the composite materials we're looking at because they are one of those few material systems that really spans the entire palette of the Gen 4 reactor systems. So the first topic I want to deal with is material compatibility issues for the high temperature liquid cooled reactor systems. And in this, proposals are being looked for to assess potential materials for construction of ASME code covered components for either lead or lead bismuth eutectic or salt cooled high temperature reactors, so that we can identify what the preferred candidate materials are for these constructions. And there are three different aspects of this work. The first is to take a look at the existing database of experimental work that's been done to determine corrosion and erosion effects of materials in these environments, augmented by laboratory experiments as part of this program, if that's appropriate, to extrapolate how much corrosion is going to occur within the proposed lifetime for the various assorted components for these systems and the temperatures and the times involved. If it turns out that that corrosion is acceptable, then that's good if it can be met with the existing materials that are within the ASME code, and I'll get into what those materials are in a moment. If it's not possible to do that within existing code materials, then what is the potential for using alternate materials or alternate design approaches, and what are the details of how to go about doing that? Now, it's important from the get-go to realize that there are only 5 alloys that are currently contained within ASME Section 3 Division 5 rules for high temperature reactor component construction that are allowed for this high temperature service: the 2 ferritic steels, 2 1/4 chrome and 9 chrome, 2 stainless steels, 304 and 316, and the 1 high temperature alloy 800H. Alloy 617, high temperature nickel alloy, will be added almost surely within about 3 years, so that will be 6, but still, that's it. Some of the other alloys which people have identified as useful and desirable for these other reactor systems, such as Hastelloy N for liquid salt service, very good, very little corrosion up to 700 degrees C, which is about the temperature at which it loses strength, would be great. Similarly, the Chinese equivalent, the GH3535 that's being developed at Synap, are not approved by the code for high temperature nuclear construction. Similarly, HT9 and the silicon aluminum modified steels, which people are looking at for lead and lead bismuth service, they're just not in the code. You cannot use those for nuclear construction at this point in time. Hence, one of the other approaches that people are looking at is putting coatings on to protect the materials that are in the code, or cladding, weld overlay cladding, for corrosion prevention. And those are interesting ideas. However, ASME Section 3 Division 5 simply does not have rules that allow for the use of cladding or bimetallic structures at those high temperature conditions. So something has to be done about that. Some of the components that we're talking about for these reactors are going to have to survive for the entire length of the reactor operation. Things like the pressure vessels are probably going to have to exist for all 60 years. Some of the other components, intermediate heat exchangers or internals, may very well be replaced every 5, 10, or 15 years. So one has to take the service life into consideration, as well as the corrosion rate, to determine if the corrosion allowance can be met with which of these materials. If you can't make it with the existing 5 materials under the service conditions that are identified for these plants, and you take the tack that you're going to want to try and approve some new alloys, you have to realize that very comprehensive and long-term testing is going to be required to do that. And the requirements for this are laid out in the new Division 5 Appendix HBBY, which has been published in the last 2 or 3 years, and anybody can take a look at it. The requirements are substantial. On the other hand, if the decision is made that a recommendation is appropriate to use a coating or a cladding, first of all, one has to show that this is viable for the life of the component. Coatings have possibilities of being scratched, spalling, and otherwise creating holidays which would lose their protective ability. Cladding has a particular issue in as much as the code requires the use of or the consideration of deformation controlled quantities such as cyclic loading and thermal stresses, and it's simply there are no rules to do that. So that portion of the code would have to be developed. So no matter what is going to be done, the pathways that would allow either alternate materials or alternate evaluation methods within the ASME code for high temperature construction would have to be defined if that approach were chosen. And we would be very interested in having detailed enough analyses made that rough orders of magnitude of resources and time and tasks be made available as part of the NEOP project so that we would understand what would be required to be done. All right, let me move on to the second task, RC3 on 6-6 composites. In this case, we're looking for proposals to develop a scientific understanding and innovative advanced methods to detect, evaluate, and predict degradation of 6-6 composites in the operating environments of the advanced reactor systems. And as I showed earlier, these are applicable to virtually the entire palette of Gen 4 reactor systems. I want to say right up front, however, neutron radiation effects are not included in this activity. We recognize that those are a very important part of degradation of composites and virtually all of the other structural materials of interest, but that work is being covered elsewhere and does not need to be included in the response to this proposal. Now, a predictive capability is the ultimate goal of this work, but we recognize that that may very well be outside the scope of a 3-year NEOP. So the development of the practical principles of degradation and or methods for in-service inspections or property determinations may be considered as a very useful type of proposal. The results from this work, however, should strongly support the code rule development for 6-6 composites that is ongoing currently within ASME Section 3 Div 5. Now, this shows, without going into any detail, where and why we are interested in the use of 6-6 composites in these advanced reactor systems. Virtually every Gen 4 system has applicability for 6-6 composites, typically as specialty parts. In addition to the Gen 4 system, even LWRs and fusion reactors have use for these. So, I mean, they're widely useful because of their high radiation tolerance, their high temperature tolerance, and their high environmental resistance. But they still have limitations, and we need to understand what those are. Some of the specific applications for composites in our Gen 4 systems include things like tie rod units, restraint straps, hot gas ducts, control rods, even in power conversion systems for things like combined turbine, blade, and disc units and heat exchangers. So we know that there is an interest in this among the vendor community and the design community, and we'd like to understand how we can predict performance and lifetimes in these things. Now, there has been work that goes back a number of years that have demonstrated the effects of load and temperature clearly affect subcritical crack growth and degradation mechanisms in 6-6. Some of the work that was done by Jones et al. Back in P&L in the early 2000s demonstrated this. We know slow crack growth in 6-6 as well as degradation in general is affected by environmental oxygen levels, fabrication processes, the state of the interfacial layers as they were fabricated and how they have degraded over time, operating temperatures, general environments, etc. So validated predictive degradation models and detection methods are needed for the range of the reactor environments that we are looking at in these Gen 4 systems. We recognize, however, that interim supporting studies to determine the fundamental effects that would be used in developing those models are very useful. All of this work, as I mentioned earlier, should be coordinated with the ASME codification activities in Section 3 Div 5, and any questions with regard to that can conveniently be directed to the technical point of contact for this work, Yutai Kato at ORNL. He is leading the charge for putting that portion of the ASME code in place, as well as a number of the related ASTM standards on the SICK materials themselves. And just as an example, you can see something that's from the core region of the pebble bed modular reactor, no longer being developed because the organization gone out of business, but it's a good example of how ASME Section 3 Div 5 needs to understand the behavior of interactive materials properties from the various types of materials. You can see a section of the core wherein the inner graphite blocks are being restrained by an external strap that is made of both metallic straps and composite straps. And so to understand and have the properties and long-term behavior of those materials is very important. All right, the points of contact for this work, myself, I'm the federal point of contact, and my contact information is there. For RC1 on the corrosion, for the liquid coolant, Sam Sham at A&L with his contact information is shown. And for the work on the SICK composites, Utai Kato at ORNL is the proper contact. At this point, if there are questions, I'll be happy to address them.
Will in situ corrosion or radiation experiments be of interest in RC1?
In situ corrosion for the liquid coolants?
Clarification is in situ corrosion under irradiation.
Of interest, yes. However, let me make sure the focus of that topic is understood. Our primary interest in that topic is to understand whether the materials that are currently in the code are going to be sufficient for building the components for those systems, and if not, what alternate materials may be appropriate, and or what changes to the code analytical and design methods are going to be required for things such as coatings or claddings. Now, if in determining the corrosion allowance that is required versus the design life, it's critical to understand what the corrosion is under irradiation, that would be a piece of determining whether the existing or proposed materials would meet those goals and what might be required to make the changes. Radiation effects are not considered by the code, but in determining what materials might or might not be sufficient to meet the design requirements, i.e. corrosion limits over lifetime, that would be useful to find out as long as the rest of that topic were addressed.
Should we consider all of the liquids, i.e. salt and metal, in the RC1 in one proposal? Would that be more appropriate for two proposals?
I believe that there would only be a single award per topic per organization. Maybe I'm mistaken on that, but I think it would be appropriate to consider all of the aspects in a single proposal, whether it was for one material, one coolant or more than one coolant.
For SICK degradation in RC3, is oxidation-assisted degradation a critical mechanism?
Absolutely.
This PI would like to confirm that graphite is not a focus of RC1?
Graphite is not a focus of RC1.
Under RC1, what are possible examples of alternate materials and design methods?
Some of the ones that I listed, just possibilities. I'm not endorsing these, but ones which I've heard the community discuss. The use of Hastelloy N for liquid salt service. It's a material that was used to build the molten salt demonstration facility down in Oak Ridge way back in the 60s, and it performed well, but it's not in the code. So that would be an example. And there are a number of materials that have been evaluated for liquid lead service, particularly the high silicon and high aluminum modified steels, which seem to have higher corrosion resistance in liquid lead, but they also are not approved for construction in ASME code. A couple of approaches that have been proposed are to take some of the existing materials, such as the stainless steels or alloy 800H or even 617 once it's approved, and coat those with a corrosion-resistant material such as nickel for liquid salt service, or even Hastelloy N as a clad layer. Some of the questions that would arise from doing that relate to the rules for design and use of a clad structure where the thermal expansion and contraction of the cladding versus the base metal would have to be considered. Those rules do not exist in the code. Another issue that would have to be considered is diffusion of species through the clad layer into the base metal, and what effect that might have on overall corrosion. On the other hand, there have been some coatings that have been proposed and developed that appear to be self-healing, but they are developed on materials that are also not within the code. So there's lots of innovative approaches out there. The question is, can any of these be codified? And if so, what would be the process in sufficient detail that we could perhaps develop a plan with the resources and time available to go ahead and put that in place so that designers could use that as we move forward over time.
As a follow-up to the question about corrosion, are you looking for long-term tests using liquid loops or short-term tests?
Well, it's a 3-year program, so I don't think you can do any long-term tests in a 3-year program. I guess that would be up to the discretion of the proposer, how they wanted to allocate their time and resources between examining the fairly extensive data that is available, that others have already done, augmenting that with any kind of testing that they might want to do, comparing that with anticipated required corrosion allowances, and then developing the modifications to get any changes that would be required into the code, along with a sufficient detail that we could understand what that pathway would involve.
Under RC3, is fuel cladding the main focus?
No, fuel cladding is not the focus of RC3. Structural materials for Gen 4 reactors is the focus. We recognize that 6-SiC is being considered as an accident-tolerant fuel cladding, but no, that is not the focus of this work. It's as a structural material. There is no code requirement for fuel cladding. The code requirements are for structural materials. However, the degradation mechanisms would be possibly related to fuel cladding work, and I'm sure would be of interest to the folks in the accident-tolerant fuel world. But no, that's not the focus of this topic.